Okay, so this is not my usual format. This is going to be old school. We're looking at pencil and paper. I just finished off explaining a little bit about the lemma, which says that edges correspond, have a one-to-one correspondent with moves that are not single-stone suicides. So the rest of that proof, which I'm going to post, is looking at how you would have arrived at a configuration Q and ruling out possibilities. So it's pretty straightforward. A nice corollary to this is that a node or a vertex with k empty points on that, a configuration with k empty points, has an outward degree, and a degree is the number of edges going out of the node or vertex, equal to 2k. So here's an example. This was from our game graph 1, 2, so we just have two spots to put stones on and only one horizontal line. This particular position has only one empty node. Now we drew the whole game graph for this particular example, and there were two things that could have happened. It could have gone to this particular, I think it's hard to see my mouse, but this particular node over here by placing a white on the empty point, and the white then captures the black and you're led to this particular configuration. Another thing you could do is you could place a black on this point, and that would suicide your original blacks. It would be a black string suicide and bring you back to the empty. So coming out of the one empty node, the number of outward edges is equal to 2, which is equal to 2 times 1, because k is 1 in this case. So we're going to look at G13 just to make a more complicated example. And what I did is I made figures because I didn't want to hand draw this and subject you to something like that. So let's look at these figures. Let's just take that one at random. And let me make this a little bigger since I can do that. So I'm going to take this one at random. This has 2 empty points. If it had 2 empty points, then k is equal to 2. Theoretically, according to this corollary, there should be a total of 4 outward edges coming out of this vertex. Are there? Yes, I can see, just count the number of arrows coming out of this red box. I see 1, 2, 3, 4, all highlighted in green, coming out of the red box. So indeed, 2 times 2 is 4, which gives me the 4 outward edges. So the corollary is validated by my experiment. Going forward, so just to summarize, the highlighted node in the red box had 2 empty points with 4 outgoing arrows, 2 times 2. What about 2, 2? G of 2, 2, that's more complicated. So I'm going to show you an example with a G of 2, 2. And I'm going to count the number of edges coming out of a particular randomly selected node or vertex. So let's go back to this. I'm just going to take this at random. Now the way they made this, created this, it wasn't me that created it, it was whoever wrote this paper. They put all the symmetries together. So this has 3 empty nodes. So I'm going to take the upper left particular configuration. They grouped them all together because it actually makes a difference. So this upper left, how many outgoing edges does it have? Well, if you just look at the arrows, I have 3. 1, 2, 3. But what you realize is that I actually have 2 arrows coming here, because if I take this black in the corner, the other black could have gone here, so I'm looking at this configuration, or the other black could have gone here, so I'm looking at this configuration. So instead of 1 arrow going here from this particular configuration, there's 2 guys that is mapped to over here. And so there's indeed 2 different outgoing arrows here. So if I count that, let me show you another one here. if I take this one up here, how do I get into this box? Well, the white could have gone up here, so that's one possible arrow, but the white could have also gone down here. That's another possible arrow. So indeed, this has two arrows coming out of it, and has a third one too as well. So if I count up all the arrows now, counting all these possibilities, I get 1, 2, 3, 4, 5, 6, which is exactly 2 times 3. So the corollary is validated. What I want you to do as an in-class assignment is see the one that I've highlighted here. What I'd like you to do is to find, so take this left one over here because they symmetrized and put them together. So take this left one over here. It has two empty points. Show me the 4 different configurations that you can arrive at from this configuration, because by that corollary there should be 4 different configurations that you can arrive by legal moves. Find them and list them. Draw them out. That's your first part of your in-class assignment. And you can pause that and work on it while you're you don't have to wait for the whole lecture to be finished. You can finish off by actually watching it. Just in case, I'm saving it. So I actually wrote it out in words here, so if you didn't understand the in-class assignment, draw the outgoing possibilities for the one I circled in blue. This is the configuration I circled in blue. Actually draw them out and show me you should get 4 different arrangements where it could lead to. And then explain how this corollary is justified. Like I just said, you should get 4 of them. Okay, give you a definition. A simple path is one that has no repeated vertices. So it's a path. You can follow a path from one vertex to another vertex that's connected through other vertices in between. It's like connect the dots. But it doesn't come back to any of the original vertices that you've already traveled over. So that's what the definition of a simple path is. The entire Go game is in one-to-one correspondence with simple paths starting at the empty position. So what does that mean, this lemma? We're going to play with it, of course. You knew that I didn't ask that question rhetorically. We're actually going to do something with it. How do I get rid of this? I don't think you can help me because you're not here. Second definition is that a strongly connected graph is one where every vertex can be reached from another vertex. And I don't know what I've done to my, let me do full screen, see if that helps. So it does a little bit. So every vertex can be reached from another vertex. Another lemma is the game Go is a strongly connected graph. So I would like to do an in-class assignment where we start with the blue and show by listing. So I'm going to show you what I mean by the blue, but we start by listing one by one how we get from the blue to the red. And so you have no idea about what I mean by blue to red, but I'm going to show you. So I'm looking at G13. So this is the mess of G13 that was drawn by a computer. I'm going to show you first an example of how I can reach one from the other. So here I've done this one and this one. I'm going to show that there's a path that connects both of these together. That's the same one. Here it is. If I start here, I get to here. How do I get to there? Because if I put a black in this empty position, then the black will kill out this white, and I arrive at this position. From this position, if I put another black here on the empty point, I can come back to the empty position. With the empty position, I can put a black on that right third corner and get to this one. So this randomly chosen starting point is connected to that other randomly chosen endpoint. So what I want you to do for your in-class assignment, and I'm going to blow this up, is actually list for me on a piece of paper the configurations you arrive at to go from this particular point, the blue, to this particular point, the red, or this vertex to this vertex. And explain to me how you, like I just did, with how you can actually get from this move to that move by telling me what game moves I have to do to make that happen. For example, if I was going to go to the empty here, I would put a white stone right here, and that would suicide everything, and I would end up with the empty graph. So actually say that in words so it's very clear to me that you understood what I was trying to do. And so that's the last part of your in-class assignment for today. It's a very short lecture, but I hope it's clear even with the different kinds of media we're using today. Email me or text me if you have any questions.